Okay, so what we've done is we've taken our question, what is the fastest we could ever sort n numbers? And we have reduced that question to something completely different, and it turns out completely tractable, completely analytically tractable. So we've taken our question, what's the fastest we can sort n numbers? And we've said, well, any sorting algorithm that uses two-way comparisons to identify how to sort the numbers induces a decision tree. Right? That decision tree is a binary tree where at each decision point of the tree, we either say yes, these numbers are sorted correctly, or we say no, these numbers are out of order. And so we can take any sorting algorithm and build a tree. And so that means if we can understand the properties of trees, of binary trees, we can understand something about sorting algorithms. The only thing we have left to do now is say, well, look, the tree has to be expressive enough to return any possible ordering or any possible permutation of the input array, which means the tree has to have at least n factorial leaves. So now we can say, look, a decision tree, or every sorting algorithm corresponds to a decision tree with n factorial leaves. So how can we make these decision trees as short as possible? So here's a basic discrete math fact that kind of relates the number of leaves of a tree to the number of levels of the tree, or the height of the tree. So it turns out that the shortest we can make a decision tree, the shortest possible decision tree with n factorial leaves, or I could even say binary tree with n factorial leaves, has a height of the following, has a height of the ceiling of log base 2 of n factorial. Okay. So what does this tell us? So this tells us that every sorting algorithm that uses comparisons to sort an array has to use at least this many comparisons. Okay, so this means that the ceiling of log base 2 of n factorial is a lower bound on the number of comparisons to sort n numbers. All right, so now let's see if we can identify if we can derive something useful about this expression. It's not at all obvious that log of n factorial is something that we can analyze, but it turns out we actually have some handy formulas for doing something with n factorial, right? Recall back to when we were first starting to talk about this stuff, about algorithm complexities. I gave you Stirling's formula that gave us this kind of limiting expression for n factorial. So let's do some analysis here. Let's say log base 2 of n factorial equals, let's just say as n approaches infinity. So this is kind of mathematically imprecise notation here, but I'm saying we can approximate n factorial when n is large using Stirling's formula, and this looks like this. So this approximately equals, oh, and by the way, I'll also get rid of that ceiling, because when n gets large, we know that the ceiling doesn't matter asymptotically. It just gets washed out. So as n gets large, this looks like the log base 2 of, now let's plug in Stirling's formula for n factorial. So 2 pi n of n divided by e to the power of n. Okay. So now we can start to use our log rules to simplify this. So we can say, well, this is equal to the log base 2 of 2 pi n to the 1/2 plus the log base 2 of n divided by e to the nth power. So this now is equal to log 2 of 2 pi n over 2, okay, which we take that 1/2 and pull it out, plus n log base 2 of n divided by e Again, we use the log rule and we pull that n out. And now we're getting somewhere. Right? So now this piece here is order log n, right? We can see that because it has that log n in there. So we're not going to simplify that anymore, but we can simplify the one on the right just a little bit. So let's just copy down the first one like this: log base 2 of 2 pi n over 2. Now plus n log base 2 of n minus n log base 2 of e. Okay, where we use the fact that log of n over e, this is an e, I don't know if that shows up well on the video, log of n over e equals log of n minus log of e. And now what do we have? Well, we've got something that's log n, something that's minus order n, which doesn't even make any difference at this point, and something that's order n log n. So this whole thing is big theta of n log n. And now what is this? Right? What does this expression say? Well, this expression says it says that every comparison-based sorting has to perform at least order n log n comparisons to sort an array. So what does this say? This now becomes our tight lower bound for the complexity of sorting. Right? And it all comes down to this tree argument. In the end, all we have to do is say there are n factorial possible decisions to possible outcomes, which means that our tree has to have n factorial distinct leaves. And then we just identify how tall does the tree have to be to contain that many leaves. And the answer is about n log n. So it turns out that merge sort is asymptotically optimal in terms of its speed. Right, so merge sort runs in this complexity class. So that means merge sort is asymptotically optimal for sorting, and it turns out it's actually pretty close to optimal. So the actual number of required comparisons is not far, or merge sort performs not many more than the optimal number of comparisons. So it's worth wrapping this all up, and so we can say what is our conclusion here? So the conclusion is that big omega of n log n is a tight lower bound for sorting. And I'll be precise here, and I'll say for comparison-based sorting. Okay, so what do we do with this, right? What's the point? Well, I would argue that there's three things that we can take away from this. So one, we don't need to waste time looking for better algorithms, right? So no need to waste time trying to improve. Right? If someone comes to you and says, I have an algorithm that sorts in linear time, right, in big theta of n time, now you can say, oh, does your algorithm use comparisons? And if they say yes, then you can say, nope, you are wrong. You do not have an algorithm that sorts that fast, because we know that if you use comparisons to sort, you can't do any better than n log n. N log n is the best you can do. Okay, so that's kind of point number one. Point number two is that we can use this to infer stuff about other algorithms, right? So this gives information about other algorithms. Okay, so sometimes what we can do is we can say, well, knowing that sorting can't be done this fast would actually let us argue that, say, merging can't be done this fast. Because if we're using comparison-based merging as a subroutine in merge sort, then now we can make some conclusions about merging. So I'll talk about that a little bit more in the synchronous session, because that's a subtle point that I don't want to spend too much video time on. And then three, this helps us to identify bottlenecks in our algorithms, right? If we know that identify bottlenecks. Let me just write this down, bottlenecks. Okay, and we'll talk about this just a little bit in the next video, but what this lets us do is say, hey, we've been very careful all along here to say the the tight lower bound for comparison-based sorting is n log n. Well, that suggests that maybe there's non-comparison-based sorting methods that are faster than n log n. Right? Maybe we give something up in using a non-comparison-based sorting algorithm, but all we know with this is that we can't use comparisons to go any faster. So that means comparisons could represent a bottleneck in sorting algorithms. Okay, so let's just examine one area where that's true with sorting algorithms, and then we'll move on to do some more stuff along this topic.